Okay, welcome to episode number 70 of the Piezo SHOCK Show, and today I'm going to be answering a question from a viewer like you regarding one of my previous webinars where I modeled a piezo material, which is anisotropic by definition, as an isotropic material in order to easily simulate that and not having to worry about putting all these different properties in. All you have to do for an isotropic material is know its density, know the Poisson's ratio, which most of the time you can like assume it's like zero point 0.3, and know the modulus. If you're working for with a bolt clamp transducer, you assume that the 3,3 modulus under the constant electric field condition is the modulus you're going to use to get the resonant frequency, and you can make an assumption that using the open circuit compliance, which can be calculated from the K33, the coupling factor in the 3,3 direction, and the original modulus in constant electric field can be calculated, because usually the electric field under constant electric displacement is not provided. You have to calculate it, but that's easy enough. So today I'm going to be sharing a question. Let's see if I can appropriately read the question out for you. Um, so a person is doing modal analysis and they like this method. They have access to the stiffnesses and compliances. Um, so the question is, hey, I'm modeling this piezo material in a modal analysis environment, but I don't have any ability to put a D33 coefficient, because I mentioned by doing an open circuit compliance and a short circuit compliance or modulus, you're able to determine a coupling factor. But how do we input a charge coefficient in order to change the coupling factor? Um, so that is interesting. Um, that so if you wanted to change you can't change the D33 and the D31 for modal analysis, but the way you can sort of input it is the coupling coefficient, K33, and I'll write it out and I'll show it to you. So K33 is equal to the square root of the actually it's equal to D33 divided by the compliance under the 3,3 direction multiplied by the permittivity. So this is actually, let's square this. Square root that. So this is what you really need to be looking at. The K33 is equal to the D33 divided by the compliance, the square root of the compliance and the permittivity. So you can actually calculate that K33 coefficient, which then, as I think I've described earlier, I think this is the equation. I'm just doing it off the top of my head because, yeah, I am. The compliance is larger, so and the same coefficients would be valid. You can just take the inverse of this. So the compliance under constant electric field of 3,3 direction multiplied by 1 minus the coupling factor squared is equal to the compliance with the constant electric displacement. And that's how you can actually, if you change this value, you would actually change the coupling factor, which then you would use to calculate the new compliance that you would get from your experimental coupling factor that you would put for your transducer, or calculate from the resonance and anti-resonance frequencies for your transducer. So there's some more questions here, and I'll just keep going. Um, so a person asked, "So does this mean I won't be able to match the coupling factor with only modal analysis?" So you can do coupling factor matching with modal analysis in the way I mentioned. If you do assume that you know the permittivity and you know the compliance. So it's a tricky thing when you actually assemble a transducer. You usually, I feel like, you get a lower coupling factor than you would expect experimentally, but it's it's not so important to match the coupling factor, I believe, when you have assembled your device, because it's going to be different for a lot of reasons. A lot of things around regarding interfaces also are affect the coupling factor. So they're not exactly piezoelectric per se, but yes, as I mentioned, as I showed in these equations, you can calculate a new coupling factor by changing the D33 coefficient, and you might assume the permittivity is the same, which is an assumption. So I yeah, so open circuit properties, you can model the coupling factor. Okay, that's what I said. So regarding the coupling factor for lead-free ceramics, the Poisson's ratio is very low. Uh, it is low. I think it is very low for lead-free ceramics. So lead-free ceramics that I have personally tested, I can't say which ones because I don't think it's like, but the ones I have tested myself, some of them have very high coupling in the 3-3 direction, but they're very poor in the 1-1 direction. So or sorry, the K3-1 direction. So um so the coupling factor for the 3-3 is usually for the, at least a lead-free ceramic that I've tested, it's much higher than it is for the 1-1 in comparison to PZT. So let's say the PZT ratio between coupling factors from K3-1 to K3-3 is a factor of 3. So the K3-3 is 3 times higher. But in a, let's say K3-3 is 0.6, K3-1 is 0.3. Let's say for PZT. But for a lead-free ceramic, K3-3 may be 0.5 and K3-1 maybe 0.1. Like, so it's going to be much lower. So the coupling factor, so the K3-1 is Poisson's ratio based. We have to remember that. There's a question on here on, so if the Poisson's ratio is lower, the coupling factor is lower. No, it's really, this is kind of highlights the anisotropic behaviors. But what I'll say is that K3-1 is dominated by Poisson's ratio. It's the primary effect you can imagine is the stretch and compression of the thickness, or the along the polarization direction. The secondary effect is actually the Poisson's ratio. That's the way I like to think about it. So yes, if the Poisson's ratio is lower, it's going to disproportionately affect the K3-1, not the K3-3. So that's what I'll say there. And the person who asked this question, I'll send you the YouTube video. If anyone else has questions, they can email me or write comments, and I'll try to answer those questions as soon as I can. But the best thing for you to do is jump on my webinar that I have every month. So go to my website, sign up for my webinar, and I'll answer questions live, even if they're not pertaining to the topic, after I'm done giving my blurb about the topic that I promised. All right, so thanks for watching, everyone. Take care, and I will see you for the next Shock Show episode. And also be sure to come to my webinars. Thank you.